Anyone? If anyone has to complain about this, talk to Thomas.
Or do
Send me an email.
Not this Thomas.
All right.
Pits.
All right, so let's get started. So you guys have handed in part 1. Part 2 is due Thursday in class. I posted a supplemental lecture that shows you like the whole process of going through the code, coming up with how you actually generate your own unique instruction memory, your own data memory.txt files that you'll be using. So that's what the main part of that is, actually take that C code and translate it into assembly and then binary code, which at this point, basically anything that I did in the supplementary video and the stuff we covered in lecture, you should be able to figure it out at this point. So today we're going to continue covering virtual memory. We're going to go over basics of what's known as a TLB, which is, for those of you who've taken operating systems, what's a TLB? Lee, what's a TLB?
A translation look-aside buffer.
Transition look-aside buffer. Then we're going to talk about how page faults are handled really briefly in the virtual memory. And then we're going to be going into multiprocessing. How do we use multiple processors at the same time? So, in virtual memory design, there are 3 things that we want to bear in mind. We want to bear in mind that the pages should be large enough to try to reduce access time. So what that means is, if we have a small page, right, and we're swapping back and forth, then the smaller the pages are, we have to do more swapping. The more swapping that occurs, that actually ends up in raising our average memory access time because of that memory access, remember? So if we're going to be swapping in a page, we want it to be large enough so that way we don't feel like we have to quickly grab another page, right? So you don't want to have instances where you're constantly going back. Again, I'm going to be picking on you, Lee, since you're taking operating systems. What's the issue when you're spending more time swapping pages than doing processing? What is that called?
Don't remember off my head. Sorry.
It's called thrashing. So thrashing is an issue where if we're not worried about, if the operating system doesn't make sure that we're actually, like let's say I do a load word operation and I do 2 load operations back to back, right? So if one's in one page and one's in another page, I'm not taking advantage of this principle of locality, then I'm spending more time actually going to get the pages than I am actually processing, getting it from the memory and putting it into the registers, correct? So you're spending more time doing that. That becomes what's known as thrashing. And in this case, we want to try to reduce this. Also, we want to try to reduce our page fault rate, which seems to make sense because we want to try to access the pages as little as possible because you want to take advantage of these high-speed caches. And third, we want to handle page faults in software since overhead is low compared to disk access time. So what this means is we're talking about computer architecture. And it's kind of this hybrid between where the instruction set is where hardware and software meet, how we take software and implement it in hardware. Well, so we start making compromises. So, for example, where we're doing error correction in MIPS, we want to make sure we're using our data forwarding unit and our hazard detection unit, right? So we're actually putting in physical hardware units to detect whether on each buffer we have the most up-to-date copy of the register. So if you did this in the non-volatile slower memory using hardware, it becomes time prohibitive. So what happens is they're actually going to use software monitors, and especially in Section 8 when we get into RAID arrays, trying to monitor each different disk to ensure that we actually have the proper amount of, that we're not allocating pages in the wrong way. So we use the operating system or use different programs to allocate that. So these are the things we want to worry about. And one way we're going to be doing that is using what's known as a page table. A page table contains the correlation between a specific virtual page number and the physical page number. So if you remember from last class, we saw this. There's virtual addresses, and then here there's some sort of magic done. Last class, you kind of just press the I believe button. Well, the page table is what actually does this physical translation. It takes it in. It kind of does this, translation here. It also stores certain values that are in the memory. So I'll get to this. Let me show you this diagram in a second. So you have this page table, and it has a valid bit indicating one that it's actually in the physical memory. If it's 0, then you actually have to go to the disk storage to do a page swap. So the valid bit is used to determine whether the value is currently located in the physical memory. I showed you example 1 just a moment ago, so you saw the difference, if you recall from the problem, that there's going to be more memory addresses than there is physical memory. Even though in modern computers that's not much of a problem, but in computers in the 1980s, early 1990s, you're dealing with 16K, 1 meg, and you have 4 gigabytes of addresses. So you had to do a lot of address translation. So these page tables were very useful. So we're also going to be using this concept of the swap space. The swap space is the space on the disk reserved for the full virtual memory space of a process. So you have a program. That program requires this much memory, and we have this much cache. Right? So if we have this much cache, we have to be constantly doing these page swaps to, get the certain amounts of the program done. The swap space in the physical memory is where our entire process is. Now, if you're using optimization, such as taking advantage of locality, trying to use as few variables as possible, that's at the code level. So that's where the fact that with computer architecture, it's visible to the programmer, system attributes of the program. That's where making sure that you're efficient in your coding translates to improved performance at the hardware level. So that reduces the amount of swap space. Does that make sense? So what's going to happen is, let me pull this out so that way for those of us who want to see better on the screen, we can do this. So you have a virtual page number. This is what's issued by the processor. Load word instruction, right? We've gone to level 1 cache, is not there. We've gone to level 2 cache, is not there. We've gone to level 3 cache, it's not there. Now we have to go to the main memory. Well, the first thing we do is we access this page table. The page table tells me, based on the address translation, whether or not something's actually in the physical memory or not. So if we have a relatively small amount of physical memory, and we have this huge disk storage, and the swap space is larger than the physical memory, eventually we're going to have to access the disk. So in our page table, you're eventually going to have instances where the valid bit is going to be 0, meaning that it's actually in the disk. So if we go to the virtual page number issued by the processor, we go to the page table. If it says 0, then I'm going to have to perform a swap. This is what's known as a page fault. It's equivalent in cache hierarchy. It was a cache miss. We go to level 1 cache, it's not there. We have to go to level 2 cache, it's not there. We go to the page table and it's not there. We're going to go to disk storage. So this is where things can take a long time. But if it's in physical memory, we just grab what we need and we send it back to the processor. And we put it into the cache hierarchy. Does that make sense? So, as I have this question here, how can we improve this? Other than reading what I have there. Like engineers, what's a weakness in this diagram? Mm-hmm. Exactly right. So let's say I'm here, right? We also have everything has to go through the page table. So we have 2 bottlenecks. Bottleneck 1, on every single access we have to access the page table. And second one, we're trying to avoid going to the disk as much as possible. So we want to take advantage of this principle of locality, right? So what happens if we had something, instead of having to access the page table, we could actually look aside and see if we have something that's these pages that have been accessed very recently and bring them in. Take advantage of that principle of locality. So that's what's known as a TLB, a transition look-aside buffer. It's going to circumvent the concept of the page table, try to look there first, If it's not there, then we have to do the address to go into the physical memory. And if it's not in there, the valid bit is 0, then we're going to have disk storage. So we're going to end up having 3 bits here to access to tell us where things are. We have a valid bit, we're going to have a reference bit, and a dirty bit. The dirty bit tells us if we've updated the data since it's been last swapped into the disk. So store word, for example. We performed a store word operation and we have changed the physical value of the variable. We load it, we store it into the memory. We've updated the page. The dirty bit becomes 1. Then we know 1. If it's 1, then we know that we have to update it in the disk in order to maintain what's known as cache coherency. It's going to be a cache coherency problem, but especially when we get into multiprocessors. So the definition of a transition loci buffer is a cache that keeps track of recently used addresses in the physical memory to try to avoid access to the page table. So it's actually a fast lookup. You go there, you look it up. Has it been recently updated? Yeah. Okay, well then I can go get it. Instead of having to do the translation. Because this is the translation. Remember this problem here? This is the actual translation that's going inside the page table. Inside the TLB, we have a reference bit, indicate whether the object's been recently referenced, right? And as a dirty bit to indicate whether it's been modified. So let me reread. Transition loci buffer is a cache that keeps track of recently used addresses in the physical memory to avoid access to the page table. So this is what the operating system is doing when you actually have to access the main memory. Virtual page number. Virtual page number is the address issued by your MIPS processor, the load word or store word operation, right? We've checked cache, it's not there. We've checked, now we have to check main memory. First thing we do is we go to this TLB, transition loci buffer. Notice how all the bits that are 1 actually map directly to physical memory. This means instead of performing a physical translation, we just see it's actually just stored there. That translation that we did in example 1 has already been done and it's stored in the TLB. So we go to TLB, hey, it's there. Okay. We go to physical memory, get it, without having to perform a translation. If it's not in the transition loci buffer, then you're going to the page table. Once you go to the page table, yeah, it's also mapped, but it's actually doing a translation. Now, in the instance, these 3 are highlighted, 0, 0, 0. In those cases, that's what's known as a page fault, meaning it's not in the memory, I haven't updated it, and it hasn't been recently referenced. Right? So if it's 0, 0, 0, that's when we have to go to the disk. So here's what happens. You're doing a store word operation. You've done something in the local registers. You've updated it. We've done an add operation. Now we have to update it because for some reason it has to be stored in the main memory. Perform a store word operation. This is because remember earlier in the semester I drew this data memory and I drew a giant question mark and I said it's a mystery. Just press the I believe button right now and you all laughed. So now this is what it is. Store word goes there. First thing, it checks to see if it's in level 1 cache to update. Is it there? No. Level 2 cache, is it there? No. Level 3 cache, is it there? No. So now we're going to go into the virtual memory. Go to the virtual memory. First thing we do is we look in the transition loci buffer. Is it there? If it is, we just return it. If not, then the next thing we do is we go to the page table. If it's in the page, we go to the physical memory, grab that, put it into the cache, and continue operation. If it's not, that means it's not valid, it's not dirty, meaning it hasn't been updated, and hasn't been referenced. We go to disk storage, and this is a page fault. We don't have the page in the physical memory, so therefore we have to go to the disk, grab the page that we need, perform a swap, update our page table to say that we have the new physical address, right? And since it's also been recently updated, what else do you think we need to update? We need to update the TLB because the TLB has the most recently used pages, right? So if we're grabbing something from the disk, you're going to update physical memory, you're going to update the TLB, you're going to update the page table, and then send it back to the processor.
Does that happen sequentially or simultaneously?
You mean like updating the physical memory and the TLB? You're going to update that. It's actually going to be, that's a good question. You're going to update it sequentially. Now the reason why, going back to let's take the concepts that we learned at the lower level of the processor and take it up to the operating system. Remember the concept of a control hazard, right? And the reason why we have to separate instruction memory and data memory is so that way we don't have instances where we're trying to get an instruction and perform a store word in a pipeline data path. The TLB is actually its own location in the physical memory. They're actually, the TLB is going to be a small part here, and then the rest of it in the physical memory is going to be here. So the first thing you do is you go here. I have it already. Good, I can send it back. But then, if not, I have to go to this page table to perform the translation like we did in example 7.1, and then see if it's there. And if it's not, then we have to go. So the first thing we have to do is we have to go to the data memory, update this location in the main memory, right? Then tell sequentially the TLB what to do next, right? And then we update the page table. So you can have an optimization by updating this and then updating the page table and the TLB simultaneously. But you're going to have to update the page table and the TLB sequentially. Does anybody have any other questions? Why is it the start? If I put 5 stars next to a TGO, what does that usually mean? Yeah, you'll see it again in the future. Yeah. I must think it's important. Sure, if you want to go with General or Admiral or 4-star. Yeah, I won't say it's a 5-star Admiral. How about that? Okay, so once the operating system, we've already described the concept of the page fault. So 7.16 is kind of what we've just described. 1, look up the page table using the virtual address and find the location of the reference page on the disk. So we find the location on the disk based on our referenced address, right? 2, choose the physical page to replace. So there are a number of algorithms that we could use to choose a physical page, and it's based on how the memory is allocated. We're not going to go into that in this course, but this is a problem that you'll address early and often in operating systems if you ever take that course. Because we've really discussed paging in this class, but there's another idea called segmentation. So paging, all of the pages are the same size. In segmentation, you're going to be putting elements into the memory that are different sizes. Right? So oftentimes they'll be allocated by functions or by variables or by parts of a program and try to optimize the use on the page. Because what happens if I have a program where that only takes up this much of the page? Well, then I have all this memory here that's not being used. So segmentation, what they try to do is they try to have a smaller segment fill that spot. The problem is, then you have to incur, on the operating system level, try to manage where all the segments are, and sometimes you quite can't get the right size. You can get a smaller segment and break it up, and it becomes a problem. But it optimizes memory use. But in the meantime, all we're going to worry about is grabbing a page from the disk and swapping it in, and choosing this particular page. Typically, we're going to use the least recently used. If it hasn't been used in a while, let's get rid of it. Now there's issues with that as well. But in this case, in this particular course, least recently used is sufficient for knowledge. And then this last part, start a read, to get the question that Hugh was asking, start a read to bring the reference page from the disk to the chosen physical page. So let's say we walk through this process, we go through, we go to TLB, it's not there, we go to the page, it's not there, we go to the disk. So now we have to choose which page in physical memory we no longer want there, because it's limited space, right? So we have to swap one out and then put the disk back in. So if it's just there, okay, you just put something in physical memory. Remember, the reference bit is 0. So now we have to reference the page we just accessed through a read. Perform a read. Okay, I went there. Perform the read, then you're putting it back into the processor, and you're updating the reference bit, and you're updating the transition look-aside buffer. So that's the third part. To start a read, let me scroll up for those of you in the back. Part 1, look up the page table entry using the virtual address and find the location of the reference page on the disk. So going back to the drawing, that's this process. Step 2, choose a physical page to replace. If the chosen page is dirty, it must be written to the disk. So what dirty means is we're using this bit to try to optimize performance. If we have a least recently used and it hasn't been updated, we don't need to put it back on the disk, right? Because it's the exact same value as the value on the disk. So you just go, is it dirty? No? Okay, well, it's the same thing. If it is dirty, that means the value is physically changed and you have to update it on the physical hard drive. And then the last part is to take that third stitch, put it into the physical memory, and then start a read, which will mean it's been referenced. It will update the reference bit, and then it'll update the transition look-aside buffer. And while you guys are writing this down, I'll read this part outside of TGO, but this is kind of tying into the whole concept of why it's so hard to implement this in hardware as opposed to software. They occur in the middle of instructions. So if you recall from previous section 6, we were talking about exceptions and interrupts. And so the exception occurs in the processor level when we have an overflow or the processor generates an incorrect opcode, right? Well, that happens in the middle of the instruction. So what we can do at the processor level is we flush it out using no ops, correct? We have all of the control signals become 0. And then we actually have to go to the IFID buffer and stop it to perform a no-op, and then we have to go to ID execution buffer to stop it, because there are no control signals in those first 2 stages. So as you can see, whenever we come up with a problem, you have to address every little aspect of it at the hardware level. How does this impact performance? How does it impact my hazards? Well, now we're going to the operating system level, and we're not only dealing with the processor, we're dealing with the physical memory, we're dealing with cache, we're dealing with the transition look-aside buffer, we're dealing with the page table, and we're dealing with the physical disks. So if you have a page fault, you're not going to realize it until you've gone instruction fetch, you've fetched the instruction decode, we've decoded the instruction, we've executed to calculate the address of the load word. We go to the data memory, and only then, in the middle of the instruction, do we know whether or not we're going to have a page fault. Right? So that's why it's very difficult, because the more you have to mitigate in the middle instruction, the more hardware you get, the more it's going to cost. And it's going to cost, you're going to have power increases, you're going to have cost increases. And eventually, the improvement in performance may not be beneficial to your customer. So what happens if the instruction cannot be completed before handling the exception? I'm sorry, the instruction cannot be completed before handling the exception. This means, kind of what I was just alluding to earlier, we have to wait until we perform the page swap, get it into the physical memory, update the transition look-aside buffer, update the page table, bring the value back into the levels of cache, right, that we specifically want, and then continue to process. So this is why data memory access times can be up to 100 times slower than cache, which is why we want to use cache in the first place. We're trying to take advantage of that principle of locality to avoid having to do this on every instruction.
At what point does the cache size become inefficient for physical memory?
So the cache size can become inefficient in one of 3 ways. If the cache is too big, then you actually have to go through and do the translation to search for the specific variable that we want. That's when it becomes inefficient. Also, if we recall from direct instead associative, you lose that associativity process, and every level of cache becomes you're going to have it. It's going to be accessed a little slower. It's going to be a little cheaper. So the amount of the size of the blocks, kind of going back to this concept of paging and segmentation. If you have a certain amount of blocks, that's the smallest amount you can translate between the levels of cache. So eventually, there's going to be times when you're going to you need to get a specific variable, like one specific word. But let's say the block is 10,000, is 1K. So you wanted 32 bits, but now you have this extra 1,000 bits that you have to put in. So you're trying to limit the size of the blocks. You're trying to limit the size of the cache itself, so you can actually get to that location as fast as possible. And you have to try to ensure that there's a good trade-off in the second and third levels of cache between speed and cost. So that's where it becomes inefficient.
So would you say it's a good size for an L3?
For an L3, well, it depends on the implementation technology. It depends on typically you'll get 4K to 16K. In these types of processes that we're learning, you'll have I think modern processors may have up to 512 megs of cache. Yeah, like I said, the processors that they were working with in the early 80s are significantly smaller. But then you're dealing with 128 gigs of physical memory, right? So 512 megs isn't, So it depends on, and those numbers are going to get bigger and bigger as our ability, as the quad cores, operating system speeds improve. Just our ability to access the cache in different ways. I mean, there's all kinds of research going on in how to improve cache access, especially in general processing units, CPUs. So. Those are really good questions. Does anybody have any other questions? All right. So, and then kind of as we've discussed before, once you handle an exception at the processor level or a page fault at the operating system level, you have to be able to restart the instruction and have it do the proper operation. So that's virtual memory. Next, we're going to discuss this concept of multiprocessing. So up to this point, we've been dealing with one processor, one set of operations. We're trying to improve throughput by doing this pipelining concept. We're trying to have multiple instructions in the data path at any given moment. So what happens if I have more than one processor? I can do multiple things. I can have one processor do one task and one processor do the other. If I'm doing something like matrix multiplication, I can use multiple processors or threads to be able to do different aspects of the calculation to make it run faster. So if you ever used a calculator to do matrix multiplication, it does it almost as fast as it comes back with an addition. That's because it's actually using multiple cores to perform that operation in an efficient manner. So we define a multiprocessor as a computer system with 2 or more processors. The objective of running a multiprocessor is connecting multiple computers to get higher performance. So the whole idea of a quad core, quad core means it's 4 processors on one chip, and they're communicating each other through interconnects and buses. And so the whole idea is that we're going to take these inefficient processors where we can, through pipelining, we can gain a maximum throughput of K, speed up of K, where K is the number of stages. Remember the problem that we were talking about, the ideal pipeline throughput? So now what happens if I want to beat that? If I want to beat that, I'm going to have to use multiple processors. So I also made a little note here. Multiprocessing is very good, particularly if you're thinking about space applications or military applications. Multiprocessors are very good for error checking. If you send a computer out to space, it has to work. It's not like, oh, well, Voyager's near Jupiter, let's just send the IT guy out, right? Can't do that. So they'll often run 3 processors in parallel, running the same operation, and then they'll use something called majority voters at the output to check. So if oftentimes all 3 of them will produce the same output. I mean, that's what happens most of the time. But if one of the processors breaks down or has a fault, it'll change. So, but if 2 of the processors are fine, that means it's still going to output, both of them will output 1 or both of them will output 0. If the third processor outputs, if you have 2 processors that find it outputs a 1, but the third processor outputs a 0, the majority voter will go, well, I have 2, they're 1, so that's the right answer. Yes?
So what would be the difference between running 3 processors in parallel and in series?
Well, if you're running them in series would mean you're doing it one time and then doing it again and then doing it again. Parallel means you're actually running them concurrently. Yeah, Adi.
For multiprocessor, do all the processors have to be the same? Like, can you have a MIPS and an x86?
No, they don't have to be the same.
Okay.
You can have application-specific processors. That do specific tasks well. So if you're a designer and you feel that the MIPS processor performs floating point operations best, but you feel like ARM processors perform other types of or other arithmetic operations better, and you feel like you want to have multiple processors doing that, yes, you're permitted to do that. As long, and this is where code comes into play for those of you who complain about coding, you have to ensure that all the processors can run the same code. And this is where an issue is. Like we're going to talk about down here, there are 2 major issues with parallel processing. You have to implement the software in parallel. So oftentimes you'll just run the same processor because they have the same compiler. But if you write code, you want the code to be able to do no matter what the processor is, right? So that's one of the benefits of the Java virtual machine, is that it takes advantage of this thing we were just talking about in terms of paging and using that swap space to use the actual physical memory as the, quote, cache, because then no matter what the compiler is, it eventually has to access the same physical memory, right? So at that binary level, it's going to be the same. However, if you've ever run a program on the Java virtual machine, you know how it runs a lot slower. That's why, because it has to access the physical memory quite a bit. So the 3 design goals for multiprocessor implementation . Oh, okay. That should have a colon there. The 3 design goals are scalability, availability, and power efficiency. So scalability means that no matter if I have dual core, quad core, multi-core, single core, and I write some code, I want it to be scalable. I want it to work on everything. Have it compile down to the specific processor. It may not have the same performance, but it should still work, right? So it can get really frustrating if you want to run a very specific program, like Xilinx, and suddenly it doesn't work on Windows 8 because it's not scalable. Not that I'm bitter. that's where that comes into play, because it's trying to run on different processors through the operating system. The operating system allocates the amount of memory that's being run, and so it has the code should be able to run on multiple operating systems. Availability means that you shouldn't have these issues where it's only running on one processor. It should try to distribute processing abilities throughout all the processors as best as possible, right? And power efficiency, you eventually want to ensure that you can't consume too much power. If you have 4 processors in a chip at once, you want to make sure that if you're using all of these processors, that you're not just burning up the computer. And there's this concept of design corners for those of you who want to take my digital CMOS VLSI design course next semester, where you have to worry about temperature, yield. How does a transistor operate? How does a set of transistors operate under a certain process variation? Meaning, you're trying to get from a 0 to a 1, right? So in this class, we went from LSI to VLSI level. And we were like, okay, there's this concept of 0 or 1, or in the 116 for standard, we're about undefined values. So what are these undefined values when we get down to transistor level? And how does that undefined value affect power efficiency? When you have undefined values, you're still consuming power, right? So you're consuming a lot of power, and the computer isn't doing what you want it to do. So you have to worry about what happens when you have issues like that in multiprocessors. So there are 2 types of processors. We're going to talk about process level parallelism. Utilizes multiple processors by running independent programs simultaneously, kind of like what you were talking about a little earlier, Adi. It permits high throughput for independent jobs. So if I have a processor that's running all my floating points, and I have another processor that I dedicate to word processing, and I have another processor that I dedicate specifically to I/O, I can use process level parallelism to do that. And oftentimes you also hear this defined as job level parallelism. So, whereas on the other hand, you have a parallel processing program is a single program that's running on multiple processors. So I was talking about matrix multiplication earlier, right? So you have to you're doing the whole process of performing all the additions and putting them into the third matrix. That would be rather inefficient if you were doing that one instruction at a time, right? I don't want to go too much into runtime. I don't know how many of you have taken algorithms yet. But you can improve that significantly by using multiple processors to improve throughput. So that's this type of parallel processing program. One program on multiple processors. And as I mentioned a little earlier, a multi-core microprocessor is a single integrated chip that contains multiple processors. And each of these processors is called a core. So before, we were talking about multiple processors on different chips that we have to connect through a separate bus. Whereas these multi-core, so whenever you hear quad-core, dual-core, anything in advertisements, they're all on a single integrated chip. Going all the way back to the beginning of the semester, remember we were talking about Jack Kilby and how he solved the problem where they thought that every single chip every single piece had to be connected. Does anybody remember what that was called?
Integrated circuit.
Yeah, what the problem was called. The tyranny of what? Tyranny of numbers, correct. Imagine how bad the tyranny of numbers would be in multiprocessors. Okay, right? So instead, you run everything on a single chip, can communicate through buses, and use the operating system to allocate memory and resources to different processes. So when you're talking about multiprocessing, you're going to be talking about 2 forms, and this is TGO 7.22 here. TLP and ILP. ILP is instruction level parallelism. And you guys have already studied a form of ILP. So I'll read you the definition. I want you to tell me what you think it is. Instruction level parallelism is overlapping the execution of instructions to improve performance. ILP relies on hardware to discover and exploit parallelism dynamically. MIPS pipelining does this. I already gave you the answer. It also relies on software technology to find parallelism statically at compiler time. It exploits implicit parallel operations within a loop or straight line code segments. So, okay, I gave away the ending there in the notes. But why is MIPS pipelining an example of instruction level parallelism? Any ideas? Let me repeat. Why is MIPS pipelining an example of instruction level parallelism? By the definition, overlapping the execution of instructions to improve performance.
Just has one path that's going to go reduces time by hard coding circuits.
Yeah, that's exactly right. Yeah, because the whole idea is.
Those will be a mechanical engineering.
But it kind of is, right? You're putting pieces together to try to run it through, but then you're running the code to statically find your parallelism. So this whole idea is that if you have 5 instructions in one processor at any given moment, well, that's more or less parallel, right? Remember our little diagrams? We had fetch, decode, execute, memory, write back, and then we have fetch, decode, execute, and fetch, decode. Looks awful parallel, right? So you guys have already learned a form of parallelism, instruction level parallelism. And so the compiler-driven encoding of the micro engine, is going to try to figure out optimally which instructions you want to put next to each other to try to avoid hazards, to try to improve throughput, where you use that data forwarding unit, the hazard detection unit, in order to ensure that we're not going too fast and we're not having issues with making sure that data structural and control hazards are not done. So thread level parallelism is, what's up?
On the overview of the pipelining structure, I didn't see any hazard detection past
HZD
the decoding level.
Right. Well, hazard detection is going to be using, I'm trying to remember exactly which TGO it was, but it's going to compare the results. This is actually a good question. So at each stage, you're going to have the 5-bit value passed to the buffer. And so the 5-bit is going to say, this is the actual value of the register I'm going to be updating. And then the previous stage, you're going to have the 2 values coming out of the ALU. So it's going to compare those 2 5-bit values that you'd be using to access the registers and say, this is the copy that I'm about to put in the ALU. And it's going to this one say, well, this is the updated version. If they match, that means we have a data hazard. Okay? So what's going to happen is it's then going to take advantage of the data forwarding unit to forward the data back to those two multiplexers. We had 0, 0 just came from the ALU, 0, 1 came from execution, and 1, 0 came from the data memory. That's how that's done. So that's actually the hazard detection unit takes advantage of that in order to be able to perform data forwarding. So I'm sorry. Did I answer your question?
I'm just trying to.
Oh, okay.
So
George?
the hazard detection unit and the forward data unit, are those more hardware or software?
Hardware. They're actually they're like comparators in the data path. Because the reason why it's hardware is because the next thing it does is it generates that forward A and forward B control signal. Any other questions?
What about data parallelism?
Data parallelism? That's kind of where thread level parallelism. You mean what you have multiple?
Like SIMD. So.
Oh, we're going to be covering that later in this section. Okay. Yeah. So SIMD is single issue multiple data and multiple issue multiple data. We're going to be covering that later. So the second type is called thread level parallelism. It is logically structured as separate threads of execution. Unlike instruction level parallelism, thread level parallelism is explicitly represented by the use of multiple threads of execution that are inherently parallel. So this I said it looks parallel, right? But it's still all in the same processor. When I say inherently parallel, that means you're performing two fetches simultaneously. You can perform two decodes simultaneously, two executions simultaneously. Whereas this is a form of parallelism that's exploiting the buffers in different stages in order to try to improve throughput. So this is what's known as thread level parallelism. And an operating system's concept of a thread is the idea of a single process being run with a single set of resources. And so to kind of touch on what a lot of you have been asking earlier, there's two major issues with parallel processing. And parallel processing has kind of really come about since, in terms of like consumer level computers that you can purchase, it's like 2007, 2008. That's really when the idea of the dual core and the quad core came to be. Until then, people were just using single processors in their laptops. And there's an issue with compiling down to compiling down from the code that you wanted to write down to the processor. Because some people have BIOS, some people have MacBooks, some people have Dells, right?
Didn't the Core TGO come out in like 06 or?
Yeah, 06, 07, somewhere in that range. Yeah. Before then, it was just Intel Pentium 4 processor.
Yep. Straight up.
Yep, straight up.
Celeron.
Yeah. So, okay. So, if I want to write code, if I want to write programs, particularly, let's take example Microsoft Office. So I want to run it on all of these different processors, right? Well, the people at Dell aren't necessarily going to share their proprietary information with the people at VAIO. People at VAIO aren't necessarily going to share their stuff with Apple, and Apple's definitely not going to share their stuff with Samsung, right? So if you're a coder, you have to worry about all of this. You want it to compile down to all the different computers. You want people like, well, I can't use it on Windows 8, so why would I use Xilinx? Good question. That is, why would I want to use that? So implementation of parallel software, we now know that software must be designed to meet the instruction set architecture. And by we, I mean you've now learned this in the course. We're writing a program that can be implemented in both sequential and parallel implementation is very difficult. Parallel software requires significant communications overhead, requiring both the operating system and the buses at the hardware level, and coordination. And let me scroll up for people in the back.
Is that why we have to? No.
That's right. Go ahead.
No.
Okay. And part two, cache coherence becomes a much larger challenge since the presence of multiprocessors, multiple programs may be trying to access the same data simultaneously. So going back to matrix multiplication. I'm taking values, I'm maybe trying to access multiple values simultaneously. Well, what happens if I distribute a program among multiple processors and I have a copy of a variable? Well, I have a copy of a variable in one cache, right? Well, if I have multiple processors, that means I have multiple caches, which means it's very possible that I can have multiple copies of the variable in the local cache of each processor. Well, I would need to see if one processor updates one copy of the variable, well, I need all of the other processors to get that same updated value before they inadvertently update their copy, right?
Is that the advantage of having the largest page tables you can?
Mm-hmm.
Just to make sure that it clusters correctly and doesn't.
Well, actually, okay, I see what you're asking. With page tables swapping in from the data memory to the cache. So if you're having multiple copies, right, now you can actually perform what's known as, we're going to be learning about this a little later, called dictionary protocols and snooping. So snooping is going to be, like I say, if you are my processors, and I'm going to be constantly asking, do you have what's your recent copy of the variable? What's your recent copy of the variable? What's your recent copy of the variable? Okay? And let's say Aaron's processor decides to make an update. I've updated the variable. Well, you can't update your copy, right? Because what you need his most recent copy. So what's going to happen is the snooping protocol is going to say, have you updated it? Yeah. Okay. Well, then I'm going to immediately update your copy.
But it checks to make sure that it doesn't need that stale variable
Yes.
the calculation first.
Correct.
Right. Is that what does that? What checks?
Oh, we'll be learning about that in more detail, but it's what's known as a Snoopy bus.
Cool.
Yeah. Oh, that's like it's like we're going to be going over it right now. Okay. So cache coherence is the. Did everybody get this? Cache coherence becomes a much larger challenge in the presence of multiprocessors, since multiple programs may be trying to access the data simultaneously. So this issue is known as cache coherence, the consistency of shared resource data that ends up stored in multiple local caches. So this is what we were just talking about. What happens when one of these local copies is updated? How do we get these values updated in all of the caches and all in the data memory, so that way you can make sure that all the processors gathering it have the most recent copy? So there's two, write through and write back are the two. Write through is write to cache and memory at the same time. So we have the three levels of cache, and then we have the main memory, right? So the concept of write through is every time, and if you're running in a multiprocessor, I'm going to update my local copy of the cache, and I'm going to update the data memory. So the drawbacks are it can be very slow, and we use a write buffer. So if you look at this diagram here, if you're updating cache and memory every single write, that's an issue, correct? Because you're slowing down your processor. So this what's known as a write buffer, these four little boxes here, we'll wait until the update's been made, and then it'll push the next update, and it'll push the next update, and it'll push the next update. So it's a buffer, so that way you can actually update the cache and go back to the processor and not have to worry about waiting for the data memory to be updated. So if you're having issues where the store frequency is less than one memory write per cycle, then you write through is a good choice. Whereas if you're doing write back, so we're going to be writing to the cache only, but then we're going to be updating the data memory in a page swap. So write through, write to the cache and to the memory simultaneously, and we use this write buffer to improve performance. Write back, let me scroll up just a little. Actually, I should do my little thing here. And then write back, you need a dirty bit for each cache block, because this tells us, has the value actually been updated? And we need to greatly reduce the memory bandwidth requirement. So here, we have a high memory bandwidth because we have to update the data memory every time, right? And then, but here's the issue. Since the updated values, if the updated values are in the cache, that means we need to have a greater control. I mean, that's going to be more complex. And what is my, Thomas Pitts, what is this device that is going to do this? What's that called? Snoopy bus. What's that?
Call it Woodstock.
Call it Woodstock? Okay. Call the dirty bit Pigpen.
Making a movie.
We make a whole. That would be the worst Peanuts movie ever. Charlie Brown and the multiprocessor. ABC's lowest rated TV show of all time.
I doubt it.
Okay, so there's two ways we can do this. We can have centralized memory and distributed memory. Centralized memory is there's just one central memory and then local copies near the processor. So we have our processors here. I'll reread write back really quick in case any of you missed it. So the write back is writing to the cache only. You write to the cache block to memory during a page swap. You need a dirty bit for each cache block. you can greatly reduce the memory bandwidth because we don't have to go through this buffer like we do in write-through to constantly update the data memory. But the control, which is what we're going to be learning about next in centralized versus distributed memory, can be more complex. So this concept of central and distributed memory, centralized memory is also known as a shared memory multiprocessor, a SMP. So here we have the interconnection network, and we have memory talks through the interconnection network, and then there's local copies of the caches right near the processor. So processor 1 through processor n, each one, the $ here is cache. And it has large caches for each processor. Single memory can satisfy memory demands of a small number of processors, so we don't want it to have too many processors. If you recall, one of the issues that we're always trying to worry about from the 3 issues is scalability, the other 2 are availability and power consumption. Central memory SMPs have an issue with scalability because eventually you're going to overload the interconnection network trying to communicate with one centralized memory, right? And it has just its local cache. Although scaling is technically conceivable, it becomes less attractive as the number of processors sharing centralized memory increases. So that's where the scalability comes down. Because if I have 100 processors and they're all trying to access the memory at the same time to get various different variables, then you have to perform different page swaps across this interconnection network, across the bus. And then all the processors have to wait as one of the processors gets it, and then the next one gets it, and then the next one gets it. And then especially write through would be very inefficient in this type of SMP on a large number of processors. So for SMPs, you want to keep the number of processors down. And then the other type is physically distributed. So you can see the difference here between a SMP and a physically distributed multiprocessor. So in the single memory multiprocessor, you have one memory here through the interconnection network, and the interconnection network then updates the cache for the local processor. For the physically distributed, you actually have for each processor local physical memory, right? And then the connection is made through the interconnection network. So it's more cost effective because instead of having to have a communication through the interconnection network in every single data memory operation, the local memory swaps are performed here. And the only time you have to go through the interconnection network is when multiple processors have the same variable. So if we have the same variable in this cache and this cache here, and I need to update one, I don't need to physically update the data memory. I just have the Snoopy bus say this one's been updated, so I need to go here and say I need to update this one as well. So it's a cost-effective way of scaling memory bandwidth, as I was just talking about. If most accesses are the local memory, reduces latency of local memory accesses because we don't have to have each processor waiting for the interconnection network for every data memory update. And the issue is you have to change the software. Let me scroll up a little bit here. You have to change the software to take advantage of increased memory bandwidth. So because they can run faster, we have to worry about performance, right? Especially when we're dealing with assembly level and machine level language. So you can see if I have a processor that's SMP versus physically distributed memory, you'd want your code to still run, right, on both of those. You see how challenging that is? So that's why, as Thomas pointed out, 2006, 2007, that's when they really started solving this problem. Does anybody have any questions on this?
What would graphics cards usually use as far as their parallel?
Well, graphics cards, that's actually a really interesting question. Graphics cards are often going to use a very specific application-specific chip inside of them because they not only want to process the data, they want to be able to process what the specific, they have to process each specific pixel and continually refresh. So you have to get the data from the processor, go to the chip, and then the processor is going to indicate this is for this particular location. So it's going to actually have kind of a map in the memory of saying, all right, so this particular sprite here, I need to indicate this RGB value. So it's going to want to run in parallel because I want to be able to update as many sprites as possible, right? So you want to reduce the lag time.
So that's pretty much specifically hard coded for functions that it performs.
Yeah, that's why you have this specific graphics card. It's graphics for application specific. Kind of go the difference between an embedded system and ASIC. ASIC stands for application specific integrated chip. So using this, you don't want it to be allocated to any other processor, especially if you're a gamer and you want your game to run as fast as possible. You don't want it to lag and then somebody comes by and shoots you because they have an application specific chip, right? You want the better performance. You want to win the game. You want to shoot the guy in Halo. So this is how you do it. You run it in parallel processing, so you're updating faster and it moves along faster with the controls that you're doing.
Graphics cards are highly parallel,
Yes, highly parallel.
like thousands of cores.
What is, just completely off subject.
Sure.
If I'm there. What exactly is a shader?
A shader?
A shader is a program that acts on many pieces of data. Often a shader works on, it's not a pixel, I'm trying to remember, it's a fragment is what it's called in NOV, I believe. But this is where you get into some data instructions. You're applying the same operations to like all the pixels on the screen. Oh, it's not quite that, it's something close to it.
So anti-aliasing.
Yeah.
Yeah, next lecture we'll actually get into a lot of like the difference between SIMD and MIMD. And so we're going to be talking about shared distributed multiprocessing. Kind of give you a brief preview of what Lee is talking about. So you have coarse grain, fine grain, and simultaneous multi-threading. So I got this coarse grain where you're talking about like different, it's allocating a certain amount to the processors. So you have different threads of operation, right? And so at this given time, thread A needs 2 units, thread B requires 3, thread C requires 3, and thread D requires 1. So coarse is just going to do first block and wait until a stall occurs, and then pick up thread B. Fine grain is going to go by clock cycle. So clock cycle 1, this is 2. Clock cycle 2 is going to pick up this one, 3, and so forth. And then D, I think you can barely see it, but that's actually D. Simultaneous multi-threading is going to actually, so this is black and this is blue, so this is black and blue here. So it's actually, if it has 4 processors, you can actually take 2 from here, then take the first 2 from here, and shove it in there. And then the last thing we're going to discuss is single issue versus multiple issue data. So this is something we'll get into next class. I want to finish directory and Snoopy protocols before I dismiss you. So we started at 7.11. So we will finish the lecture at 7.27.
Let's change what?
Was that 7.11 through 7.27 somewhere?
Yeah, can you get back up to 26? Real quick?
Yeah.
Software technology.
And so the cache coherence problem, I'll leave this at the top. I think I've alluded to this a number of times where you have different copies of a variable in multiple processors. And so one of them is updated. And what happens if the second processor needs that data immediately? So if I have a physically distributed where each has their own local cache and local data memory, and we need the Snoopy protocol to indicate where each variable is, and it's going to say, how do I, you have a copy of the variable, you don't, you do, you don't. He makes it update, oh hey, before you do anything else, you need this. So so the reason why it's called snooping is because I'm actually snooping on all the different operations to make sure that they're done in time.
So it just buffers to where it evens out.
Yes.
Okay.
And so processors see different, oh yeah, so I've described all of this. Cache coherency defines the values returned by a read. Cache consistency determines when a written value will be returned by a read. So I update a value, it's written, and then I need to read it again. So a directory-based coherence utilizes existing cached hardware, like the invalid bits, remember the valid and invalid bit, 1 and 0, to maintain cache consistency. This approach allows state of coherence and consistency to be more distributed, but introduces higher delay, as CPUs must request the bus. They have to request the bus, like a Snoopy bus has not yet been updated. So the whole idea is that it's going to utilize the existing cache to say, hey, I have an updated copy. We need to update these variables. But it has to go through the bus to check the invalid bit. Is this bit valid? Yes. Okay. Is it a dirty bit? Yes. Okay, well then I actually have to get this copy before I actually go. Whereas snooping, a Snoopy bus protocol, can help ensure consistency across the caches. It works by monitoring, snooping, the different caches and overseeing what operations the processor performs on the data. So I have a difference here. The write through and validate is an example of a Snoopy protocol. So the Snoopy protocol is going to see that this value's been updated, this value hasn't been updated, and it's going to say, whoa, before you do anything, processor 3, you need to update your copy. And so this value is 5 and this value is 4 because it's been added. So you need to update the 5. Now, in this interconnection network here, each processor has its local cache, it has its local data memory, and it has a directory indicating which variables are being operated on. So the Snoopy protocol is going to go through here and see which variables have the same are in the directory. And if this processor here updates its variable, it's going to update that in the directory. And the Snoopy protocol, this processor 2, changes. And processor 8 is about to do this. It's going to go, no, and stop it and get the most recent copy. So that's exactly what it is. So the homework was 7.11 through 7.27. Okay, so I think there were 2 groups there. Somebody came in late and had their project submission. Please bring those up to me. You are dismissed.